Okay, and the answer is zoned iron-rich tourmaline. We're going to talk about New England magmatic mineral systems today. Will be a step back from the previous two talks, talk in much more general terms about the evolution of New England over time, the general broad character of the mineral systems that are associated with that magmatic evolution over time, the contrasts between north and south, and also some of the issues that would assist in the resolution of those factors of distribution and some suggestions for future work. I love the geology of New England. It doesn't kind of love me back quite as much with a rich panoply of Tier 1 deposits, but I can afford to be very patient. The New England fold belt extends from Newcastle down New South Wales up to Townsville in North Queensland. It's the most, it's the easternmost extant origin of the Tasmanide system and represents the culmination of a series of extensional and compressional events over time. It's rifted off to the east, and there's some debate about how much of it is missing, but we see bits and pieces, bibs and bobs around the southwest Pacific. The western part of it has this very extensive sedimentary basin system associated with it, and there are other magmatic elements further to the west even that can be considered part of the New England story. We all claim these zones, although they're outside the traditional area of the New England Orogen, we do claim them for the motherland. There is a long magmatic history from the Cambrian, but essentially firing up from the Devonian right through to the Cretaceous, and then younger magmatism as well. It's usually divided into two parts. That's because of this Triassic to younger sedimentary basin, Clarence-Morton Basin sitting on top, and that we have a state border running through, almost dividing that as well. So we have the northern New England origin up here and the southern New England origin down there, but it's all part of the same origin. But interestingly, from a metallogenic point of view, it does mark a very stark contrast between the two, and the overall complexity in the evolution between the north and south is also stark as well. So as we say, there are elements of the New England origin that are probably rifted off to the east. One of the major issues dealing with that was a lot of those were Permian in age, up to Cretaceous in age, and exact analogues of that, particularly with the East Australian ophiolite belt that we'll talk about later. Didn't seem to have the same matching ages, but Luke Milan at New England University has subsequently found Permian age tonalite trondhjemites in the dunites at Barraba here, which are the same broad age as some of these ophiolite systems out to the east. There are suggestions of bits and pieces of a younger origin as well, but in future better mapping and dating might help to resolve that. But New England is the last major extant one that we have in the Tasmanides. A lot of ways that you can divide the history up. Kim Jessup did an extraordinary job a few years ago of synthesising all the literature during her PhD studies at Macquarie University, and we're going to follow her timing today. Some of them correlate very well with existing major events like the Hunter-Bowen orogeny. Others are a little bit different, and it will always be part of an ongoing debate. But initially we start off with a transition, of course, from the Lachlan-Thompson to the appearance of New England and Eastern Australia, and remember the Tasmanides just represents over time the progressive sweeping up of stuff coming out of a long-lived Paleo-Pacific set to the east. So that represents that part of the history. Then we go into two major cycles of compression, extension, and relaxation. The first is the Currabubular Connors Arc. The second one is the Hunter-Bowen. So those are major ones that are associated with significant magmatic development within the arc. Kim Jessup put together this sort of happening diagram trying to show the evolution of source materials into this. Some of the data is a bit iffy, but a lot more work is going to be done on that space of characterising this to see whether a lot of it is continental remagmatisation of older continental materials or new addition to the crust with the building up of crust during those magmatic cycles. So if you start off in the early Devonian, Calliope, Gamilaroi terrain, it's represented very well up in Queensland by the Mount Morgan Tone Light. It represents the abduction or joining on to Australia of a Siluro-Devonian arc associated with copper and gold up in that part of the world. And then we have very dismembered bodies down in the south here in the Gamilaroi terrain east of the Tamworth belt, a lot of spillites and keratophyres and the like, but not a lot of igneous activity has been preserved at the same extent as North Queensland, and we'll look at the evidence for the very intraoceanic primitive nature of those rocks a little later on. The second stage is this sort of Currabubular Connors Arc, where we set up in that upper Devonian to upper Carboniferous time a long-term continental arc, and we can see the roots of that we presume to be these Carboniferous granites exposed down in the south here, but you can see in the geophysics up through Queensland there, possibly reappearing further to the north, although I think the New England fold belt from an isotopic and chemical composition point of view of the granites really does stop at about Townsville. These are being in place up there about the same time, but probably in a response to the same thermal event. Mainly I-type granites of the Carboniferous arc are preserved. Interestingly, where they do outcrop from Mudgee down to the coast, there's a strong metallogenic change from copper moly gold through moly tungsten in the Bathurst, Phillip, gold bismuth around the Oberon granites down to actually tin on the coast. Hygiene John, who did her work at the ANU, demonstrated in the oxygen isotopes in the zircons as you head to the south there, they get significantly heavier, indicating more continental crust is involved, and right down from about here south, you start to appear, you get the first of the Ordovician or the Lachlan zircons appearing as restite. So it appears that there is a reduction in the oxidation state as you head to the southeast, going from copper moly gold up here down to tin on the coast, and it appears to be a crustal contamination from older Lachlan rocks. Most of the inherited zircons here are actually from the Devonian plate that we assume was placed under New England at the time and was melted to form these granites, although now they're located within the Lachlan. Moving up from that, we have the first sort of major event. We have granites, mainly S-type, down in the south. This is the uppermost Carboniferous to lower Permian, where we have gone here with continued subduction. We're heading into sort of a rift phase with the cessation of that continental arc. We have S-types down in the south here, very juvenile ones, but in the north, up in the Uranus, we have a major I-type batholith, and also a significant amount of volcanics as well. That includes things like the Bolganonas and the Lizzie Creeks and those kind of things that explorers will be well aware of. Are very well endowed with various types of gold deposits, although the intrusions up there are very sparse in terms of any metal associations. Elsewhere, quite a bit of bimodal volcanism that we see repeating itself in the New England fold belt in the northern part, but we don't see in the south. We then move into a period of quiescence in the upper Permian from about 280 to 265, very little aged from that time, particularly in the southern part. The Drake volcanics come in, completely distinct. There's also a major oroclinal folding event going on, which Greg mentioned, and some relatively sparse magmatic and volcanic activity up further in the north. But this would be seen as sort of a relaxation event with a general decrease in the amount of magmatism going on, Drake's being a notable exception. Following that, we then have the major phase of magmatism in New England, the so-called Hunter-Bowen Orogen event, Permian up into the mid-Triassic, massive amount of magmatism and volcanism going on both in the south and north. The major I-type granites of the south here associated with a whole range of elements that are associated with very felsic rocks, and up to the north, copper moly porphyries, iron skarns, silver lead moly porphyries, and even PGEs in some of the layered mafic rocks. And then finally up into another period of relatively quiescence as the system dies down. We've shown the arc is progressively moving away, and by the late Triassic up into the Jurassic, things are pretty much starting to shut down. Bit of a flare up again in the Cretaceous, but many people will argue that's not really part of New England. It's more of a New Zealand type of story as the things step further to the east, but it's important from our point of view that copper moly porphyries, mesothermal gold is associated with them, and mafic systems. Very little in the south, but very significant in the north, particularly the far north. So even from going through that, you see in the northern part of the New England fold belt, this superposition, this constant complex repetition of magmatic systems, where in the south it's a very much more simple system. S-types in the early Perm, bang, huge amount of I-type magmatism. So it's a very diachronous system from north to south in terms of that, and also in the metal associations. And just to summarise again, we're representing over on the New England side here this progressive younging of magmatism across the Tasmanides. There's always got to be one outlier, Dorridilla, but generally that eastern younging, and New England represents the culmination of that. In terms of magmatic output, we can plot all these sorts of things up, although I think the amount of dating is underrepresented in the northern New England, so that tends to diminish some of these younger age zones. Someone has obviously been running amok for years down here using a state government's shrimp allocation, so that's tended to distort the values a bit in that regard. In terms of isotopic evolution, New England is radically different to the rest of the Tasmanides in how juvenile it is. So in terms of mantle growth curves up here, yes, we have the Ordovician of the Lachlan fold belt, but the Mount Morgan tonalite and the rest of the New England fold belt, they're very, very young and very unevolved. So that doesn't necessarily mean it's all come out of the mantle. It means that mantle materials have been cycled very rapidly within the crust in order to produce those isotopically unevolved ages. It's a Devonian mudstone near Tamworth. It's more isotopically unevolved than most of the granites in the Lachlan. It doesn't necessarily mean to be isotopically unevolved. It's coming straight out of the mantle. So you need to sort of keep that in mind. It's a very young fold belt. In terms of fertility, if you take all the granite analyses and plot them up against things like a fractionation indicator like potassium rubidium, highly compositionally evolved rocks, hot colours, and we look at the oxidation states here, we find that there is a parallel in the metallogeny that we see that in the northern New England fold belt, regardless of the age of these things, and we see quite an age range here, they tend to be oxidised and they tend to be compositionally unevolved. The granites in the southern part tend to be very evolved and also quite reduced, particularly south of the Stenthal granite complex. If you look at heat production in terms of potassium, thorium and uranium contents, it's chalk and cheese between the north and south. These are the kind of compositions you expect with tin granites, where here this is compositionally cold, unevolved sort of stuff, but again, relatively oxidised. And in the East Australian context, of course, you can see that association there, it stands out. They're relatively oxidised belt of rocks, and relatively unevolved. So in terms of copper associations, it's a bit of a no-brainer. That's where we would expect a lot of copper, and for tin, tungsten, moly fits the bill and is coincident with the kind of compositions that we see elsewhere in the Tasmanites. So Mount Morgan, very sodic. It's a true tonalite system there. Very, very low K rocks. It's not an alteration feature. They are genuine tonalites. They're compositionally exactly the same as the rocks from New Britain. It is a primitive oceanic island arc. Rocks that have been rafted in as part of that early Devonian process. If you then keep that separate from the rest of the porphyric coppers that we see in the northern New England fold belt, there's a whole bunch of them from the Permo-Triassic right up into the Cretaceous. Uniformly tend to have very low grades. Some have quite nice tonnages, but very, very low grade. They're starved systems. Some of them are still being explored. Mount Caninda, there's a new resource available for it. But a lot of them, this is in the central Queensland here, you get them along linear belts associated with linears and major structures, close geographic association with iron skarns. They're doing all the right sorts of things for a continental margin, continental arc type porphyry copper moly belt. It's just that they're very starved of grade. Here's a good diagram here from the USGS databases showing the Queensland deposits compared to other ones from similar locations around the world. So why is that? If you look at the geochemistry of that northern New England, they are sitting in a fertile window here in terms of potassium-rubidium ratios, certainly a lot less evolved than the granites in the southern New England, and certainly less evolved to the granites further north in Queensland. Perhaps a little evolved, but otherwise they're sitting in the right window. In terms of oxidation states, could be a little bit more oxidised, but sitting in the oxidised space as well, quite a lot of them, particularly the uranas further to the north, and coincident where, say, Jeremy Richards in his compilation of work has demonstrated that there should be good potential. And of course, if you put them on these sorts of plots, they're sitting by and large where you would sort of want them to be. So there are complex factors here why these things aren't higher grade. As David spoke earlier on, there's a whole range of factors that encourage the retention of copper, sulphur and gold in these things. We need to really look in more detail as to what's either gone wrong here, or are we looking in the wrong place, or is the exploration that was taken on a lot of these places in the 1970s needs to be revisited with much more modern concepts. Northern New England also has a range of very important epithermal systems of various different ages. That's the Mount Rawdon system there, showing a beautiful association with bismuth and gold there, so there's good potential for those sorts of things. That's the Mount Rawdon there. I've just put that in because I reckon that's a really good picture. That's off the Evolution website. I'm sorry to Midnight Oil, they can be very beautiful things. So Drake, yes, as we've said, another epithermal system, completely different to the voluminous volcanism that's occurred after that. Fantastic work by Grace Cumming, who got in there and mapped stuff that I wouldn't even get out of the car and climb down to look at. It was terrible, terrible tiger country down there, but she did a magnificent job. And the lantana and ticks. In fact, we tried to sample up the top here and came up out of the gully with more ticks than we had toofs, but anyway. I'm just getting too old for this. But Drake Volcanic, so she's put together a fantastic history there. White rock and red rock, we've done shrimp dating there, we're going to do ID TIMS, but it's all within the same age. We can be clear that they're part of those high-level dacite and intrusions. They're not a younger thing from the Triassic granites that have been superimposed upon the Drakes, and the Drake volcanics are significantly older and different to the rest of that Permo-Triassic magmatism. They've got all the things, the crustiform veins, low iron sphalerite, beautiful textures, serious acid mine drainage issues, all the genetic indicators of those sort of epithermal systems. There's also epithermal silver elsewhere in New England and at Silver Spur, some systems there which may be associated with the granites, and a lot of the Permo-Triassic granites themselves in their own right have very high silver contents in some of the deposits as well, currently being explored by Thompson. So down in the south, although we see this north-south change, there is an east-west change in the south of the New England, intrusion-rated gold belt, Timbari, Uralla and the like with moly, then to tungsten and slightly further west range of tin deposits. The tin deposits themselves, we have huge systems that are very spread out. That's 5 kilometres for the mole. We have a lot of tin through New England there, classic zone systems, tungsten, bismuth out through to lead, silver and zinc. A lot of the economic stuff, of course, is not in the presently exposed granites because they've had their roofs taken off them. The mole granite, I would say, is where 200 to 300 metres too late from what would have been one of the great tin-silver systems of the world, but the roof has gone except for a small remnant pendant, which probably has one of the world's largest hard rock fluorine resources, and that's the lowest part of the roof. Most of the systems that are of interest are where the granites are still buried, and we have these sheeted vein systems like Great Britain and New Britain, Pound Flat and other places as well. So the mapping of the distribution of granites out underneath the volcanics will be very important in looking at future metallogenic potential of these things. The mole, of course, is the classic system. Is it an extreme fractionate of the I-types? So would there be more of them around the place, or is it unique? Unfortunately, we've done oxygen isotopes on the zircons from the mole, and we find that it's actually very distinctly different from the other mineralised granites in the southern New England. It's quite heavy, not as heavy as the S-types, but would suggest that it is contaminated with crustal materials, which has made it reduced, which has brought in fluorine, lithium, which has energised it in terms of fractionation. So it would appear to be quite unique. It doesn't represent an ultrafractionate of these kind of rocks. So we can now treat it in terms of an exploration concepts or trying to look for equivalents of it as a completely different magma class. Ironically, the only other I-type one we've found like that is this enigmatic Dunboy-Gragen granite out to the west. There's only tiny little bits of it actually exposed. This is from subsurface geophysics, but it's also similarly isotopically heavy. Other issues with New England, we have tin systems which are clearly magmatic hydrothermal due to the crystallisation expulsion of fluids, but we have others that seem to have distributions of tin occurrences across a whole range of granite types that give ages that are significantly younger than the host granites. The mollies that occur within the Gilgai are the same age as the Pluton itself, it's strongly oxidised, but all these tin ones are significantly younger. So I think in some of these cases we have tin systems that are being generated by the circulation of hydrothermal cells which have picked up tin and deposited them into granites which may in some part have been their sources, but other might be quite a cold wall porphyry type environment. So for Elsmore, gee, that's a no-brainer. That's a tin granite. But these other two that are host of significant tin deposits in the Inverell-Tingha area are clearly not what you would consider. I think titanite is your clue here, that hydrothermal fluids coming through and altering these rocks will be sequestering tin out of titanite and putting them back into veins. The other interesting issue that tin in those sorts of deposits tends to be magnetic. In fact, a lot of the magnetite occurrences from our metallogenic mapping is in fact magnetic cassiterite. It's just that people didn't think that cassiterite could be magnetic. So I think there's implications there for being able to identify the source of tin from whether it's from these recycled systems versus these primary tin systems associated with their interaction with relatively oxidised granites where they may have sequestered tin from the magnetite or from titanite. Another very unusual factor about the tin granites of New England is they tend to be very flat and pancake shaped. You can see that on the geophysics where they have radiometric signatures consistent with them being very evolved but actually magnetic beneath them because they're just sitting as thin films. The mole granite is 40 kilometres wide. They're basically pancakes. To do that they have to rise and sit beneath something, and we think that's the the Wandsworth volcanics. Beautiful mapped example of that is the work that the Queensland Geological Survey has done on the Stanthorpe sheet, where all the individual phases of the Stanthorpe granite has been mapped, and if you look in the relationship between those boundaries with the topographic surface and that kind of thing, you can see a beautiful system of the progressive build-up of those large pancake things through the sequential intrusion. But they're coming up to a level there, and we've always suspected that it's the Wandsworth volcanics, the huge volcanics were to blame for that, but it appears that new dating that we've done has demonstrated a very intimate relationship between those mineralised granites and the volcanics. We first noticed this by looking at the coal seams, the dating of coal seams in the Sydney-Gunnedah-Bowen Basin, and finding they're coming out as exactly the same ages that we were getting out of the granites and volcanics in New England there, Bluff Rock, pretty much the same age as Nobby's Tuff, for example. And we've published this work because in Nature, this has come out yesterday, because what's happened is that the dating of these things have shown that it starts about the same time as we start to see major changes in ocean carbonate and oxygen, the amount of biota on the planet at about that time. That all starts to go haywire about 7 million years before the PT, the huge permatropic extinction event driven by the Siberian traps. And it appears that the arcs, continental arcs around the edges of Pangaea have all started to fire up about this time. And this is causing the stressing before that catastrophic event. Zircons from the Wandsworth volcanics have been found in over most of eastern Australia, constrained only by the presence of rocks that would contain the tuffs to actually date. So globally significant event, New England going up. Very, very important. It makes Yellowstone look like Yellowstone, basically, because Yellowstone's bigger, but it's a very globally significant event. So why is a granite geologist interested in correlation of coal beds with volcanics? Well, don't think of them as volcanics, think of them as lithostatic load. So in New England, over a period of only around 4 million years, we've had several kilometres, and Luke and I will argue whether it's 4 or 10 kilometres, of volcanics dumped on New England at the same time that resurgent magmatism is coming up, forming these large pancake deposits. But it's not just pancakes. We have intrusions up into the volcanic pole. Glen Eden is a classic case of a Bolivian-style system, or Bolivian without the silver. And if you look at the changes that occurred pre-253 and post-253 with the eruption of these enormous volcanic pole in central New England, it means the surface at which these things will allow volatile exsolution, stockwork, vein formation or brecciation, if it's close enough to the surface, rises significantly in the crust over a very short period of time and into the volcanic pole itself. That's a recent example there. So Porphyry, Glen Eden there, a lot of porphyry and dicite, USTs, the whole range, classic system there. Porphyry, dicite, we can map it. We've scanned all the holes, brecciation going on there. I think these are the kind of things that we can map buried in the pole using gravity and mag and airborne hyperspectral studies to map those porphyry and dicite outflows. There's also the ophiolite belt. Little work has been done to actually bring this together, but Gideon Rosenbaum of UQ and Luke Milan are developing an ARC linkage proposal to look at this. There are a range of whole rock types from tonallisis to pentanites. Little work to actually bring it all together has been done on an origin scale, but they hope to do that in the next few years. And some critical mineral potential in some of these things, chromites, nickel, scandium, laterites and the like. Gordon Brook in New England there, copper out to cobalt zoned porphyry as well. So in summary, it's a classic orogenic system where all the appropriate bits for an orogenic system are in about the right sort of place. CF the Lachlan. So New England's very well behaved in that regard. It's been extensive magmatic history through its age, through its time. There's been a lot of mineral deposits associated with those, but they contrast radically between the north and south. There's superposition of copper gold, epithermal gold in the north, and tin tungsten in the south. So they're very different. There's a good opportunity for exploring volcanic plutonic connections in the New England fold belt for epithermal gold silver up in the north, for epithermal tin in the south. I think if we can unravel that pile, and I think there are other older systems there that may have become a little bit forgotten, that may be worth exploring in terms of future ideas and concepts. Thank you very much, and I apologise to